How's it going, guys? Today I want to go over another LeetCode question. Today our question is called delete nodes and return forest, and this is a question that's being asked by Google right now. Alright guys, today our question is called delete nodes and return forest. Again, this is a question that's being asked by Google right now, and our problem description says, given the root of a binary tree, each node in the tree has a distinct value. After deleting all nodes with a value in toDelete, we are left with a forest, or a disjoint union of trees. Return the roots of the trees in the remaining forest. You may return the result in any order. So in case that was confusing, all we're basically doing is we're given a list of things that we want to delete from the tree, and that's based off a value of a list of numbers called toDelete. And we're also given a tree, and we're just saying anything in toDelete, if any node in the tree has any of those values, remove it from our tree and return basically references to the nodes that would be remaining after we've done all that processing. So let's walk through our example here. In example 1, if we're given this tree here by reference of root, and we're given a list of numbers to delete which contain 3 and 5, we would basically return this. So again, this is just a list of nodes that hold references to all the remaining nodes in the tree that would not be removed. So again, just walking through it to make more sense. This is our tree to begin with. We're asked to remove nodes that contain values 3 and 5. So we'd be effectively removing this 3 here, but we want to keep references to 6 and 7, which is why they appear in our output. And then we'd also be removing 5 because 5 is in our list toDelete. So we're really returning a reference to this one because that contains references to 1, 2, and 4. And then we'd also be returning references to 6 and 7 because when we remove 3, we don't want to lose those references. So hopefully that makes sense. We're basically walking through a tree, and for any node, if it contains a value that's in toDelete, we remove it. Cool. So then we're just returning every reference to a node that is left in the tree after our processing. Great. So hopefully that makes more sense now if it didn't before. And our constraints just tell us a couple different notes. So the number of nodes in a given tree is at most 1,000. Each node has a distinct value between 1 and 1,000. The number of things we're asked to delete cannot exceed 1,000 items, and toDelete contains distinct values between 1 and 1,000. Okay, so I think the first thing to think about when we approach this kind of problem is we need to realize, or at least I think about it, is processing it bottom up. Okay, and what I mean by that is that if we try and go from the top of the tree and move down, removing things, we're potentially going to actually lose things that we need references to, right? So there's no way I can get to this 6 and 7 here in this diagram unless I've gone to the 3 first, right? If we're going bottom, top, down. And if we're trying to remove things, right, there's a very good chance that if I'm doing things top down, once I get to the 3, I realize I need to remove it, and then I no longer have references to its children. So I think that a better way to process this tree is to do it bottom up. And what I mean by that is first let's go all the way down to the very bottom of the tree. So we're now below the leaves and everything is null, right? All the children of the leaves are going to be null. And then we could start moving back up, and every single time or any level where we have a node, we want to ask the question, should we keep this node or should we remove this node? So to do that, we can basically do any kind of tree traversal. I'm going to choose a DFS here. So again, we're going to move all the way down the tree, eventually get to below the leaves, and then return null, right? So we have a base case, we return back to a previous recursive call. Now we'll be at a node, and we can start asking our question, should we keep or remove this thing? So that's a general gist of how we're going to do this problem. Let's start getting into our code and putting it down in the editor. Okay, so the first thing we definitely need is a return value, right? And we're asked to return references to all the nodes that would be remaining in this tree. So we could just make a list of tree nodes, and this probably makes sense to call it remaining, and this will be a new array list. Okay, awesome. The next thing that I want to do just as a pre-processing step in our shell function here, before we call a recursive function that's going to do basically all of our work, is I want to just transform this array to a hash set so that we can very quickly determine whether or not any node's value is inside of the list of things that we need to delete. So currently, if we actually use toDelete, any node that we need to check if it's in this list or not, we'd have to walk through the entire list. So that's not super convenient, so I'm just going to turn this into a hash set so we have O of 1 access as to whether or not something should or should not be removed. So I'm going to make a hash set, and this is going to hold integers, and this is all the numbers we need to delete. So I'm going to call it toDelete, and this is a new hash set. Okay, awesome. Now again, just pre-processing stuff, we just need to take everything that was in toDelete and throw it into our hash set. So I could say for every integer I in toDelete, I just want to add it to toDelete. toDelete.add, and I'm going to add I to it. Great. Now, if you guys have been watching my channel a lot, I like to do this thing where I just have like a very simple shell function, which is what we're writing now. Then we're going to call a magical recursive function that does all of our work basically, and then return whatever results from that recursive function. So now we're going to call a recursive function, and we'll write that in a minute. So we'll say remove nodes, because that's what this recursive function is going to do. And basically to remove these nodes effectively and correctly, we need three things, right? We need a reference to the tree, so we need a reference to the root. We need to know whether or not we should remove things, right? So we need to know whether or not we need to delete any node based on a certain value. And then we also need remaining, right? Because anything that should stay will stay. And we need to basically add anything in a recursive call that should stay to our remaining. And then we also just need to return our remaining. I also want to add, before we start writing a recursive function, because we are asking the question bottom up, right? We're processing the tree bottom up. I want to make sure that when we get back to the node all the way at the top, we don't forget to ask the same exact question for the node. The root rather, and that question is, should we keep this thing or not? So in our shell function, we're going to have one more check, right? So we want to keep the root, right? Or I really should say we want to add the root to remaining if its value is not inside toDelete, right? So transferring that logic into code, we're going to say if toDelete does not contain the root's value, then we need to add to remaining, right? So we'll say remaining.add root. Great. And then we could simply just return whatever is left, whatever's remaining. Awesome. So now we actually need to do the meat of the problem, which is writing this recursive function. So let's first write our signature. So we could say public. It's not going to return anything, right? All it's going to do is add things that should stay into remaining. This function is called remove nodes, and it's going to take a tree node called root. It's going to take a hash set of numbers, of integers I should say, called toDelete. And then it's also going to take a list of tree nodes called remaining, which is basically going to hold all the nodes that will be remaining after we've done this processing on the tree. Great, so we said we're going to go all the way to the bottom of the tree first. And so we definitely need a base case once we've hit that bottom level. So when do we want to stop, right? When we want to stop is when we've gotten below the leaves of the tree, and we know that we've gotten below the leaves of the tree if the current thing that we've traversed to is null, right? So if the root or the current thing that we're on is null, we just want to return null. And otherwise, what do we actually want to do? Well, if we're not inside that base case, we want to continue moving down to it, right? So we could really easily just say root.left is equal to whatever the recursive function of its left subtree returns. So now we're going to make a recursive call, remove nodes of the root's left child. And again, we just need to pass the same things, right? We need to know things to delete. We also need to pass our list remaining. And then we're going to do the same thing on the right subtree, right? Because this is a DFS. We have to traverse the entire left subtree and the entire right subtree of the current node. So we'll say root.right is equal to remove nodes, except we're just going to go right this time. So root.right to delete and remaining. So if this is confusing, that makes a little bit of sense. Recursion can be confusing, but basically what we're trying to say right now, the flow of this whole program is going to go like this. We're going to traverse all the way down, 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 right? We're going to get to the children of the leaves, which are going to be null, and we're going to return null in this base case here. Great, so now what we've really done is we've assigned, in the parent recursive call, we've assigned the leaf's left child to null. And now we're actually sitting at a node that has a value, right? Because we hit that base case and we bubbled back up into the parent recursive call. So now we need to actually ask that question, right? Do we keep this thing or not? So now we're definitely sitting at a node once we've gotten to line 33. We definitely have a reference to root.value because, again, we have a node. And we want to ask, should we keep this thing or not? And so how do we actually determine if we should keep something or not? Well, we need to look at our hash set toDelete, right? So if the root's value is inside of toDelete, so if toDelete contains the root's value, then we have some sort of processing to do, right? Because we need to make sure we remove that value. But if it's not, right, if we don't need to remove the current node, we could simply return the node as is. So we could say return root. Okay, so that's kind of the different branches of logic here. We either keep the thing or not, and that's represented by this if statement. So if we need to delete it, we definitely need to do some sort of work, and if not, we could simply return our root. But now let's say we do need to delete the current node that we're on, right? So that's like being here at this 3 inside of our picture. And so the first thing that we need to do before we remove the 3 is we need to make sure we don't lose anything below it that we should be keeping, right? So because we've come from below the 3, right, we had to have moved from the 6 first. We had to come from the 6 first because we're bubbling back up, right? We're going to the bottom of the tree before we do any processing, and then we're bubbling back up. So we just need to simply make sure that if the left child is not null, right? So if the left child's not null or the right child's not null, that means that in previous recursive calls, we have not removed that value, so we need to make sure that we add it to remaining. So that means that if root.left is not null, then we need to add it to remaining, right? So we'll say remaining.add root.left. And again, I know it's kind of confusing, but the reason for that is because we came from that 6, right? If we're at this 3 now, we've definitely passed this 6 because we're going bottom up in our tree. So if we haven't made this thing null, that means that it's not something that we should have removed, so we need to make sure we keep it, which is why we're adding it to remaining. And now we need to do the exact same thing, but for the right child. So if root.right is not equal to null, we're going to say remaining.add root.right. Awesome. So now, again, the last thing we need to do, once we've actually saved its left and right children if they exist, is to remove the node, right? And so to remove the node, all we have to do is return null. Because now once this returns to its parent's recursive call, remember that's going to be the result of one of these recursive functions, one of these recursive calls, so we'll be effectively assigning a parent call's left child or right child to null. Great, so now once we've actually done this for the entire tree, right, we've basically gone all the way down the tree and moved back up the tree asking that question, should we keep or not keep any values? Hopefully we will actually have in our remaining on line 23 when we return all the different references to nodes that should stay after we've removed nodes based on toDelete. So now to quickly talk about our runtime here, what are we really doing? So for time complexity, we're basically calling a recursive function that's going to traverse the entire tree, right? And we're only calling that recursive function once, we're only calling it on line 18. So I would say that the runtime is O of n, where n is simply the number of nodes that we have in a tree. Now for our space complexity, it's a little bit more interesting, but I still would probably say that it's O of n. So let's talk about our reasoning here. We're definitely going to use extra memory because of our recursive calls, right? We're doing this recursively, it's a DFS, so we're definitely going to traverse every single node in our tree. And if we just had a tree that looked like a giant linked list, we'd be having n different recursive calls or n different levels in our recursion. So I'd say the space complexity is also O of n. We also have hash set here that we're using, right? And that's going to be as large as our original array called toDelete. So I think you could technically say that the runtime of this is O of n plus m, right? So n for the recursive calls in our tree and m for the hash set that we're making. But I think a reasonable assumption would also be that toDelete shouldn't be larger than the tree, right? We should at most have as many things toDelete as things we have in the tree, which would technically be 2 of n, which would simplify in big O notation to O of n. So I would probably say in an interview, I would probably mention that, but I would ultimately probably at the end of the day say that the runtime is O of n, where that's the number of nodes in our tree, and the space complexity is O of n, where again it's the number of nodes in our tree. So hopefully that makes sense. Let's run this code and make sure that it works. I meant to make this return tree node, sorry, because we're changing actually the references to our trees. So that's why, right? This has to return assigned, like what we're assigning children to. So we need to make it return a tree node. Sorry about that. Now let's try to make sure that it works. Awesome, and it does. So guys, that's how to solve delete nodes and return forest in Java. Again, it's a question that's being asked by Google right now. If you guys enjoyed this video and found it helpful, do me a favor and leave the video a like and subscribe to the channel for more. And I'll see you guys next time.
100 on my wrist, 80 on my wrist, 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 zeros, 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 80 on my wrist, 100 on my wrist, 80 on my wrist.